at which point he slowed down because he was winning. So the rest of that question, the bottom asked you to show a graph of his rates, show a graph of his speeds at which he was running using those numbers you had from above. So using the dx equals 0.001, the smallest one of the rightmost ones in the chart, we're supposed to be graphing correspondence points, meaning ordered pairs where each point represents a relationship between two things. In this case, it would be the time since the start of the race and his speed then, rate of change of distance with respect to time at all those various points. And I left it blank so you could scale this however you needed to fit this on there. But it was asking us for the graph of his rate of change. So not a repeat of the graph that you saw before, but one that would use these numbers as the dependent variable values. So near the beginning of the race, he had low speed near 2 point something. And obviously, when you're doing a by hand sort of sketch, as opposed to plotting points in GC, you're not able to get accuracy to hundredths of a second, no matter what you do, probably. But whatever you might have rounded to. So about 2, 3, 6, 8, 9, 11, 12, 12 and a half, back down to closer to 12. If you're graphing those as the dependent variable values in a relationship between time and those, you should have ended up with a graph that looks kind of like, let's see, where do I have it? Oh, it's at the bottom of this, that's right. Kind of like this. So the red dots represent my versions of points. I put scales on the axes that I typed out. But his speeds were up to around 12, 12 and a half, but starting lower. And then it's the remaining part of the directions said, after you plot those, to plot where you think all of the rest of the correspondence points are. Remember there's a question on your test that had a graph with a few points on it and asked you how many points are in the graph. Remember that when you're drawing a graph, you can plot some points in specific to help you draw it or to highlight some specific points, but the entire, the line, all the curve that goes through those, that's representing all of the other correspondence points, all the other pairs of, in this case, time since the start of the race and speeds. This was just an example of, I don't even remember how many, 9, 10 different speeds that we computed. And there are lots of different points in time in the graph that we didn't represent. Those are represented by, well, I just kind of connected the dots. So I came up with a curve that looks kind of like that. So it would go through these. And I could have gone like zigzag in between these or something, but that would indicate he's running kind of like a crazy person. Faster, slower, if his speeds were jumping all over the place. So just as a reasonable guess, say, well, maybe this is a kind of smooth or direct connect the dots sort of thing. So no abrupt changes like that absolute value graph we were looking at where the rate doesn't exist at a single point. So there's not going to be any points where he doesn't have a speed. He's not that powerful like a black hole. But if we look at this, it maybe seems reasonable if we have these few red dots indicating the calculation results that we got as their heights at the various points in time, scaled along the bottom here. So something like this, where the in-between are just numbers we didn't calculate, but somehow we had to get from 2.11 meters per second up to whatever this was, 3.6 something meters per second, probably by accelerating along the way, by his speed increasing. So what we're moving on to next, because our actual, if you've looked at chapter 5 in the textbook, the focus of it isn't calculating speeds or calculating rates of change. If you've looked at this, you'll see that you're given information that looks like this. Given rates of change or graphs of rate of change functions and asked to recreate what happened because of that rate. So our goal right now in the course is to start from knowing how fast something's changing, whether it's Usain Bolt or the amount of water in a bathtub or whatever it might be. Looking at how fast something's changing and being able to get from that how much of that something we have. In this case, it wouldn't be something we have, but it's how far has Usain Bolt run. If you just had this, you'd probably still guess that he ran 100 meters because, well, it was a 100-meter race. But looking at this, I could see from this, oh, well, he started out slow, but he got faster and faster and faster. That doesn't really tell me how far he ran. I need to look at some values. If I said, well, he's running about 2 meters per second for a little while, for the next half second, if you think about these rate of change in our small moments, just like we were doing earlier, if he's running about 2 meters per second for a half a second, he'd go about a meter during that half second. All right, so now I can picture him a meter farther down the track than he was when we started. But then I can say, well, after a half second, he's definitely not going 2 meters per second. He's all the way up to 3 or 3.5. So maybe I'll imagine he's going 3.5 meters per second for the next half a second or the next 1 second. So we can use these rates, each one used for a small moment, to estimate what happens because of that. Now, if I think that the rate is doing this, there's not a full half second during which he was running at this 2 meters per second. It's just for a small moment, maybe a tenth of a second or a hundredth of a second would be an appropriate length of time. That's going to be inefficient for mental estimating. Computers are good at mental estimating that way. Their minds work a lot faster than ours do. But if I can just use a few points, a few different examples of rates, and come up with a reasonable estimate of what happened because of that, then maybe that reasonable estimate is close enough to what I need. Or I could refine the way I was estimating to come up with something closer if I needed something closer. Now in this case, we know the end result is he ran 100 meters in this 9.68 seconds, 9.58 seconds, whatever it was. Don't have it on here. But in any case, what we're going to be looking at then is not things where we had to calculate the rates ourselves, but where we're given the rates to start with and working the other direction. So we're working from knowing how fast something's changing, whether it's position on the road, water, and know how fast it's changing, and we're going to work on how do I estimate then, and then how do I make a better and better estimate until I can find out as exactly as I need to how much of something I have, how much is accumulated because of that rate, whether it's accumulating distance or volume or mass or whatever it might be. If it accumulates at a certain rate, I can use the rate itself to recreate how much I have. So that is where we're headed next. And so, just to start this, recap the moments. I just mentioned a moment ago. When we're talking about using a rate as an estimate for a little while, we're going to use one constant rate for a little bit. Pretend Usain Bolt was running at 2 point something meters per second for a quarter second. We know he's actually accelerating, but it's only a quarter of a second. Maybe our estimate won't be too far off. Or maybe we'll end up overestimating later when he's decelerating. So in any case, this moment around x equals a is a small interval that we're using as our independent variable. The dependent variable can be whatever, but the moment we choose based on the independent variable, a small interval of that. And what we're going to do with this small moment is assume, erroneously usually, but assume that we've got a constant rate for an entire moment. Now, it's not that it's completely wrong, it's just that it's not quite right. Just like with the Usain Bolt, you could see that the rate of change was varying a little bit, but if that little bit of variation is small enough that it doesn't matter, then we're close enough. So this moment, we're choosing to be small enough so that we have something that's essentially a constant rate within it. The differential, when we see that term, or the symbol dx, is a small variation in that x or whatever the independent variable's symbol may be that occurs within that moment. So it's not necessarily the whole moment. Like maybe we chose a moment of 0.001 seconds, and we let x vary by half of that, half that length within the moment to measure what this constant rate was. So the rate of change at a moment, or the rate of change in a moment, we get to say that that exists if we can do what we did with Usain Bolt. If we can zoom in close enough, visually speaking, or calculationally speaking, if there's a small enough interval so that within that interval, the rate remains essentially constant. So the rate of change of our dependent variable, y, with respect to x, whatever the meanings of those might be. So if we could zoom in close enough so it looks like a constant speed for Usain Bolt, then hey, I can say that a rate of change in a moment exists. Now, like I said, we're actually going to be starting looking at graphs of rate of change functions, where the correspondence points in them represent what those rates are, as opposed to representing how much we have, like how far from the starting line. We're going to be looking at graphs where the dependent variable is the rate of change. So this graph on the left, red line going straight across, horizontal line, says the rate of change of the amount of water in a tub at t minutes. So this red graph is a rate of change graph. I don't know if you can see the y values there, but it looks to be at about a y value of 1.5 going straight across. It says this is the rate of change of the amount of water in the tub in gallons per minute at t minutes. So what's the independent variable in this graph? What's the units of it? Minutes, and it's represented by symbol t. Well, there's no t in the picture, but it says underneath that we're going to use t to represent that number of minutes, and it's at t minutes since whatever time 0 is. Not fully defined here. What about the dependent variable at 1.5? Yeah, is that gallons? No, it's not gallons, it's gallons per minute. So in the graph on the left, the red line graph, as time goes on, would it be correct to say that the tub is not filling? No? The tub is filling? Yeah, the tub is filling. At what rate is the tub filling? 1.5 gallons per minute. Now look at what this graph looks like. It's exactly a horizontal line, although this is a graph of a rate function. So this isn't a rate of 0. This is a rate of, look at the dependent variable value. This is a rate of 1.5 throughout. So this is a graph of a rate of change function where the rate is constant, or it's a constant rate of change. Constant rate of change functions look like that, horizontal line, because the dependent variable value is the rate. So if I have one rate, my dependent variable should not be changing in value. It remains a constant. In this case, 1.5. So my tub's filling at 1.5 gallons per minute. So the graphs on the right both represent not rate of change functions. These represent a how much of something we have sort of function. And both of them, and again, I know that the tick marks on the axes are a bit small to see, but both of these represent graphs where the rate between the vertical change and the horizontal change, dy to dx change, is 1.5, or 1.5 to 1. Or in other words, they could be representations of, and I'll make them representations of, how much of something we have. So we're starting from a rate of 1.5 gallons per minute. If I want to represent how much water I have, it would have to be increasing at 1.5 gallons per minute. Both of these graphs on the right in purple show something that increases at a constant rate of 1.5 gallons per minute. How could they both represent that when what's the difference about the starting at 2 versus starting at 0? What could that mean? Yeah.
The one was where the tub was, they started filling it empty. The second one was really water in it because they started adding more.
Yeah, exactly. So we've got one we could think about filling the tub when it's empty, or one starting when it's already got water in it. As I said, with the t here, it doesn't really fully define what this t is. It's just minutes. T is measured in minutes. So maybe this is minutes since we started filling the tub, and the top graph would represent that the tub is empty when we started filling it, and the bottom one would be there was water in it and we started adding water after that. It could also be, I don't know, there's probably some other explanation for what we could have, minutes since noon, and one tub, like maybe we've been filling all over it, and one tub we started filling at noon and it had been empty. The other one we started filling before noon, and so at noon it isn't empty. So it could have been sitting there, or it could have been just accumulating prior to time 0 at some rate or another that we're just not aware of. But we're going to be creating both of these sorts of functions from our rate of change functions. You need more information sometimes than others, depending on, is there any water in the tub to start with? Or are we starting from 0? Another thing I could talk about is just, in terms of this, how much has been added since time 0. So I could represent the top one just as the number of gallons added to the tub by t minutes. So maybe not worrying about how much is in there altogether, but just how much I've added since I started caring. So how much has been added since noon, regardless of what happened before. And the other one maybe represents how much is in there altogether. But I could talk about either of these sorts of situations, either starting from 0 or not starting from 0, and then accumulating afterwards. So it doesn't matter whether I necessarily start from 0 or not. I can do both of those situations from the same rate of change. If we're talking about Usain Bolt, he should have started from 0, otherwise he's cheating. Unless our value of t was not time since the start of the race. If it was time since a point in time during the day, or time since the second person crossed the finish line, or something, there's all sorts of ways we could write the independent variable slightly differently and end up with needing to have a slightly different result. But something like this top, which is labeled the number of gallons added to the tub at t minutes, you can always just think about, well, what is actually accumulated just due to this, and not worrying about where we're starting from, how much there was to start with. We could just graph the additional, or if it was something that was decreasing, how much it's decreased by in total since time 0. If you have additional information, you can start from someplace else. But a rate function on its own can at least give us this sort of idea, how fast I'm accumulating. And if I have additional information about where I'm starting from, what initial value I have to begin with, or something like that, we could have a variation on that. But the rate of change of the two of those graphs on the right would be the same. So the names for these, because of this sort of interpretation, the top one where I'm just going to imagine starting from 0, not worrying about what was there before, or it doesn't have to be starting at 0, 0. Whenever I'm starting my accumulation, just start the y value, how much I have, start that from 0, beginning at whatever time x value-wise, or t in this case, is of interest, or whatever the problem specifies. I can always start accumulation from 0 and just refer to that as net accumulation, how much has happened since I started counting anything. Versus the other, sometimes called the total amount or total accumulation, just how much altogether do we have of something, where how much you started with would certainly be important. But notice that the rates of change of these two are identical. So this is the simple case of one constant rate all the time. But the only difference between those two is, graphing terms-wise, vertical intercept. But it's just the starting point, that initial y value, the very first y value. Do we start and only care about what happens after that? Do I start from a dependent variable amount of accumulation at 0 and build up or down from there? Or do I start from some other previous accumulation, some other known value that happened prior to information I have about my rate? So we're going to run across these words: rate of change function, net accumulation function. We're going to spend most of our time on those. That's the meat of it's in there. And then there's just a one number difference between that and our total accumulation, which is where do we start from. So not a constant rate. Suppose that this function r sub v, and notice the notation. This was used on the Usain Bolt function also. The function that described where he was on the track was function f. And then at the bottom, it asked you to sketch values of r sub f, the rate of change of function f, or graph his speed at a few different points, and then we did the connect the dots game. We're going to use this notation, an r, with a subscript that represents what we're measuring the rate of change of. So if I have a volume of oil v, I can talk about the rate of change of that volume of oil, r sub v. So if function r sub v gives the rate of change of a volume of oil expelled per day by a rig, and that rig began leaking at time t equals 0 days. So taking a look at this graph, again, this is a rate of change graph. This isn't how much oil has leaked. Because that wouldn't make, if this were an amount of oil, that might not make sense. Oh, there's a large amount of oil that leaked, and then there was less oil that leaked. That doesn't really make any sense. This is how fast in cubic meters per day the oil is leaking. So rig springs a leak, it's leaking quickly. They try to stop it from leaking. It's still leaking though throughout all of this. I've got positive cubic meters per day. So that's some that leaks at any point in time. Or at any moment, there's a positive value for how many cubic meters per day have leaked. But what we're going to work on is trying to figure out how much leaks. So I've got a, let's see, copy of this. We're going to take a look. So I've got lots of graphs and numbers, and so in order for you to see the numbers, I'm going to give you a version that you can see a little bit more up close. It's going to match what you'll see on the screen over the next, this class period and probably part of Monday. But if what I'm trying to do is figure out maybe how much oil leaked over the first couple days here. So there's two sides to this, a lot of information. Some of it's going to be a little overwhelming. Some a little overwhelming for just right now. Anybody need more?
Yes, we need more over here. I only got one. This is just like
Yes. Yeah. This isn't something to turn in. I just have a lot of details, and I don't want you to stress out trying to copy down a lot of graphs and numbers and things, so I'm going to have it up close. But, so this is a rate of change graph. Let's say I just wanted to answer how many cubic meters of oil leaked over the first 2 days. During the first 2 days here, if I needed to know how much leaked, I'd need to use my rates. So maybe you could pick out some rates. Like, well, it looks like it started around 28. Looking at this visually speaking. And then, well, I know by a day in it was down to maybe about 5 or 6 cubic meters per day. And then it went back up maybe around 8 cubic meters per day. So you can just pick a number in between. Say, well, kind of like if you're driving down the road and you're like, well, I know I was going between like 40 and 60 miles an hour, so let me just pick 50. If I went 50 miles an hour for half an hour, 25 miles. Not a great estimate. So what we're going to do is try to develop ways to get, make this kind of a regimented way to go about this, so we can have a regular pattern and get estimates. And that way we can also program GC to help us with this and take a look at how to make our estimations better. But just visually speaking, graphically speaking, if I wanted to create a function for the volume of oil that had spilled since the rig started to leak, thinking about drawing the purple graphs from the previous slide, the how much has leaked. There's a positive amount that's leaked. We can track it that way. But would it start from 0 or would it start from something else in terms of our initial point? At time 0, would I have 0 oil spilled or some other amount of oil that had spilled? Yeah, at time 0, if this is since the oil rig began to leak, I should have a graph that starts at 0 cubic meters have leaked, and then increases from there, right? It's going to increase all the way, or increase only some and then decrease? If our oil is, this represents our rate at which it's leaking. Well, let's see, it's got to start from 0 cubic meters leaked at time 0, and then go up because there's oil leaking, so I've had positive amount of oil leaked in cubic meters. It's got to keep increasing. The oil doesn't unleak. It keeps leaking. But if you can think about how these correspond to one another, the first part of this graph has relatively fast rates indicated between like 20 and 30 cubic meters per day for the first little bit. So if it's leaking at a rate of between 20 and 30 cubic meters, then not doing any computations, but just it's got to be going, the amount leaked has got to be going uphill. Over the next little bit, maybe I could say, oh, well, over the next while, still within the first half day, the rates are down to between 10 and 20 cubic meters per day. So I should have more oil leaking, but there should be less later in the day than earlier in the day, right? So in the first, I'm just going to draw a point here, just as a rough rough estimate. Apparently it doesn't like me today. All right, in the first, what is that, first quarter of the day or so, all of the rates in this first quarter day, first 0.3 of a day, are all between 20 and 30 cubic meters. So over the first quarter of a day, I'm definitely going to be increasing the amount of oil. Don't worry about what these Y values are precisely. It's going to be going uphill. During the next quarter of a day, my rates are between 10 and 20 cubic meters per day. So if this were driving, this would be, we slowed down, right? But we're still going forward. So the oil is still leaking, but just during the second portion, maybe not as fast as during the first portion. So we went uphill because it was oil leaking, and then went up again, but less during the next section. And I could break this up into whatever sort of intervals I wanted to and do this. Like, oh, well, during this section it was between 10 and something. So this graph, if I look at it, is going more across and less up, or the ratio of up to across, dy to dx, as I go across this graph here is becoming less and less and less until about here, at which point it seems to get a little steeper at the end. Thinking about how that matches up with this graph, I've got a positive rate indicating oil leaked is increasing throughout, but it's increasing quickly, and then increasing at slower rates. Amount of oil leaked is increasing at slower rates. Slower rates kind of flattens out where it looks like they might have had it under control here, is about to go down to not increasing, but the lowest rate in this whole graph is maybe about, what is that, 2.5 or 3 cubic meters per day. The oil is always leaking. So this graph of how much oil is leaked would always be going uphill, indicating more oil is leaked over time. But it just goes uphill at different rates. Or in other words, what we were doing with the Usain Bolt stuff is you started with the graph on the right, and we recreated the graph on the left. We're trying to do the reverse now, because that process is maybe more familiar. Look at something, figure out the slope, the steepness, how fast is it changing. But if you look at a graph that shows a function whose dependent values are those rates, can you piece back together bit by bit, or at least think about in general what the accumulation, in this case, of oil spilled will look like? So that's what we're going to be working with over the next few weeks, up until your next test, which is October 3rd, so about 3 weeks from now. We're going to be starting from a rate function and figuring out how to recreate and all the details involved with sketching graphs maybe, but also dealing with the functions themselves and how to represent how much has accumulated, whether it's oil or anything else, due to a given rate. Starting from how fast something's changing, how do I figure out how much of something I have? So thinking about these graphs, just make sure you're always very careful when you look at a graph. What is this graph representing? What are the independent and dependent variables? So this is representing a rate of change of oil spilling in cubic meters per day based on an independent variable of time measured in days. So if I say this function r sub v, the red curve, r sub v of 0.7 is 9.68. That's talking about, I don't know why it keeps going back to that screen. That's talking about a point on this graph someplace. Well, it's a point on this graph when the independent variable is 0.7, the dependent variable is 9.68, so it's that point, approximately. What is the 0.7 referring to in context? 0.7 what? Days. After 0.7 days of the oil spilling, what is this? Yeah, the rate. It's the rate of change. So at that moment in time, 0.7 days into the oil spill, the oil's leaking at a rate of 9.68 cubic meters per day. And again, this doesn't mean that in the next day, 9.68 cubic meters are going to leak out, because this isn't a constant rate. I can see that this rate is decreasing. But what it does mean is that for any small amount of time that goes by, within a reasonably small amount of time, the amount of oil leaked would be 9.68 times that number of days, whether it's 0.001 of a day or whatever you want to say. You can make a very small increment. But if I talk about in the next thousandth of a day, 9.68 times that much, which would be, what, I don't know, 9 thousandths of a cubic meter of oil would leak, approximately. So I can see that this is not a crazy function. It's not one where if you zoom in, it's actually like snowflake shaped or anything. It's just this polynomial sort of, nice smooth curve graph. So if I were to zoom in closer to that, I can imagine it looks not crazy. I could almost imagine it looks like a constant rate. But let's see. Hello. Can I get this to, there we go. So this is what you have on the first diagram on your paper looks like this. So you've got this correspondence point, 0.7, comma 9.68, indicating a point in time and the corresponding rate. Or how we can use this, in a small moment around this time, 0.7 days, the rate of change of amount of oil spilled with respect to time is changing at a rate of 9.68 cubic meters per day. Or the amount of oil spilled is changing at that rate. I suppose I should make English sentences. So we're using this as an essentially constant rate, like we were talking about with Usain Bolt, and that when we had his distance and we zoomed in to find something that was essentially linear. Linear functions for an amount of something represent constant rate of change of that amount. What do constant rate functions look like again? We saw one already today. Constant rate functions would look, if I had a constant rate of change and I were looking at a rate of change function, horizontal line. All right, does this graph from a distance look like a horizontal line? No, not very much. If I zoom in, zoom in, zoom in, zoom in, I know it's never going to become an exactly horizontal line because it's definitely going downward. But if I zoom in so that it's like 0.0005 units from side to side, the graph from this distance, I can tell it's dropping, it's going downhill. If I'm in that close, depending on what scale I put this at even, it could be nearly horizontal, meaning nearly a constant rate graph representation as long as I look at a small moment. So if I zoom in right here, this looks like a straight line, but that's not what we're not looking for just generally straight line. If we had a rate function that was actually representative of a constant rate that was graphed, it would need to be exactly horizontal. We don't have exactly horizontal, but zoomed in this far, if you can see, this is 9.8 and this is 9.6. So in this small moment around time 0.7, which goes 3/1000ths of a day to the right and left, you can see those numbers on your sheet, the rate only changes a little bit. So I can imagine getting a not too bad of an estimate for the amount of oil spilled by using a rate that's maybe something in the middle, like about 9.68. An exactly constant rate would be like what this blue line is. So no, we don't have an exactly constant rate. I could zoom in farther and farther and farther and make them look more alike. So for instance, from this level of zooming, and I know it's going to jump on me again. From this level of zooming, like right here, those two graphs look like they're right on top of one another. It's not just a single point. It doesn't look like a single point where they cross. It looks like they kind of blob on top of one another for a while. So I can imagine, oh, well, right there, really close to day 0.7, a smaller moment, yeah, those look about the same. And I could zoom in farther and see that they're still not the same, but then there's maybe a larger section where I say, yeah, these are about the same. So I'll use this essentially constant rate for a small moment around time 0.7 in order to estimate what's happening around time 0.7 to the amount of oil that's been spilled. So and this is where we're going to go with this next week. We've got a little bit of time left today. But the idea is, if I use this essentially constant rate, if I have a starting point, how much oil there is at time 0.7, and then I assume that that rate remains constant, approximately 9.68 for a little bit, then I can figure out how much more oil there is after a little bit, after that extra amount of time has passed. So for instance, it says suppose V of 0.7 is 13.15 cubic meters. Under our assumptions here, this essentially constant rate in this moment of about 9.68 cubic meters per day is the rate at which it's changing. Say, oh, well, let's see. Let me push these buttons again. I think I'm going to have a better program next week. We found one, but I haven't had a chance to play with it yet. So if at time 0.7, there's 13.15 cubic meters of oil that have spilled already. Prior to that, there was less. We know it starts from 0 and it goes uphill at varying rates. But just suppose that I knew this one particular initial value of amount of oil that's spilled so far. These vertical values, this is my amount of oil in cubic meters, and this is my amount of time, oh, sorry, I was putting the units down, in days. So we've got days around 0.7 and cubic meters that include 13.15 and some above and below. But if we say that we know after 0.7 of a day there's this much oil spilled, 13.15 cubic meters. If I wanted to know what's V of, so remember R sub V was the rate of change of function V. V is the thing that was changing. V is the amount of oil, the volume of oil. R sub V was how fast that's changing. So if I want to find V of 0.7013, that means I want to find a value of that volume a little bit later than where this dot is. It's at time 0.7013. So here's 0.701, 0.702. So let's see, 0.7013 is maybe about here. If I want to know the amount of oil, I need to know how much change has occurred in the amount of time that's passed, and then I can compute, because we have a rate, the amount of oil that's accumulated during that amount of dx, that dt I guess is the variable here, the amount of time that's passed. This, generically speaking, dx, or I can call it dt since our time variable is t. How long is dt? What is this small amount of time that's passed between this V of 0.7 and V of 0.7013? Yeah, 0.0013, right? So 0.0013 is the amount of time that's passed to go to the right to this independent variable value. And we have our rules, right? We have, well, dy, in general terms, dy equals mdx. We can use this if we have a constant rate of change. In our symbols, dV is going to be mdt. Same idea though. If we have a constant rate that we're going to be using for a small interval, and ours is 9.68, if I go forward a little bit in time, I could go backwards also, but this is by 0.0013, I can figure out how much extra volume of oil leaked during that small amount of time. Now this isn't 0.0013 seconds, it's 0.0013 of a day. So maybe it's a few seconds, maybe it's a minute, don't really know. But a small portion of a day in any case. So relative to amount of oil leaking, probably a small amount. But if I wanted to find how much oil leaked, I could, find my dV value. Because during this moment, I'm assuming there's a constant rate. It's not exactly constant, but right around this, my rate isn't too far out to 0.7013. It's not too far from being the same as it was at 9.68. So scale-wise, I'm not going to be off by very much. It's going to be a close estimate, and I can always make it better by picking smaller variations in time. But I can find this new value of V if I have the original one. Thinking about the second half of this, I can find the change in the volume during that 0.0013 days, and I can also find Y final, Y initial plus dy, where dy in our terms is dv, Y initial plus this extra change. So if this was at 0.7 comma 13.15, then the second point is at 0.70013, or no, 0.7013, comma, well, add this amount of change, add this dV onto the previous 13.15. And it's not a nice number. It's the 13.15 plus our dV, which is 0.0013 times 9.68. So tedious computations, but symbolically, it's the same ones that we were working with before. Our V final, which in this case, V of 0.7013, would be our V initial plus dV. Or V of 0.7013 is V of 0.7 plus our extra that we just calculated due to that rate. So between now and Monday, what I would like you to do, and keep this, the sheet of paper that you got, keep that on you. We're going to do the second side of this on Monday in class. But see how there's a second value? What I'd like you to do, actually calculate out the approximate values for 0.7013 and 0.702. I didn't do the computations, but you can do those between now and Monday. Take a look at the second side, and I'll post some other things. But I've got one more thing for you, a highly important quiz. Make sure you're here on Monday to turn this in. You're going to be turning this in lecture on Monday. It does have a spot for your recitation day and time on it. Don't leave without one of these.